I'm really excited about this evening's topic. It's a really great pleasure to kind of introduce Ramy Nasser, who's our special guest and who's an expert really in two things really. So, AI machine learning, but also in design thinking and sprints. So Ramy is a Canadian engineer, designer, and author. He's the former managing director of design strategy for Architect and also head of innovation for Mattel. He's led teams in the creation of disruptive new digital products, services, and platforms. Ramy currently leads a digital studio called 1,000 Days Out that helps organizations leverage emerging technology to transform customer experiences. With his background in computer engineering and design thinking, Ramy has straddled technical design, business-oriented roles for clients, including Cadillac Fairview, Apple, Air Canada, Facebook, New Balance, Rogers, and CIBC. He's a regular speaker at international events, including the World Usability Congress, AI Everything, Machine Learning Exchange, AI Business Summit, and the World Mobile Congress. So Ramy's currently teaching design thinking at McMaster University and in the Masters of Engineering and Innovation and Entrepreneurship program at Ryerson University. He's also the author of an upcoming AI product design handbook that's set for release in late 2020. I'm really excited and appreciate Ramy coming on to the Design Sprint Network and to share his knowledge with us. So I hope all of you can give a warm welcome to Ramy as he currently does his presentation for us and also shares an activity with us in this masterclass. So Ramy, thank you so much. Really appreciate you coming on.
Let's have some fun here. Okay, what's up everyone? Hello, super excited for tonight. What I spend most of my life doing. So let's get started. Let's dive right in. Does anyone know what a zettabyte is? Doesn't even really matter that much. It's a boatload of data, just an absolutely unfathomable amount of information that we're collecting. There's tons of cliche stats and data points about how much that's going to grow over the next couple of years, and that's really not the point here. I think what I get really excited about and the potential I see in this grouping of technologies, AI, machine learning, deep learning, they're all interconnected terms. They all somewhat overlap with one another and somewhat intersect here and there. Everyone's got their own definitions, but what I really get excited about is it helps us understand, make sense of the data, and when used right, unlock some of the insights, let's say, buried deep inside of these massive amounts of data. That's the really cool stuff. There's a lot of different ways that we can look at AI, and what I'd like to do today, with all of your permission, this is going to be really, really short. I tend to teach a half or full day course on essentially this topic, that intersection of design thinking, product leadership, and emerging tech. We're gonna scratch the surface here and there, have a little bit of fun, do some activities together. But you guys can direct me. You're welcome to unmute and tell me to go faster, go slower. I do think some common understanding of the core principles of really what is machine learning as the primary facet of AI is valuable for everyone to align on. But with that, there's a few ways we can kind of chop this landscape apart. And one of them, which we're not going to spend a ton of time on, usually we spend about half an hour just on this alone, is looking at it through a use case landscape. So we can look at kind of what are the end value propositions and parts of applications, maybe not even entire applications, that AI can enable. So when we talk about recognition, for example, what are we talking about? Object recognition. So that's being able to look at a photograph or a frame of a video and understand, hey, there's a bus in that image, or there's a crosswalk in that image, there's a baby in the middle of the street in that image. Why do I say baby in the middle of the street? Well, of course, for self-driving autonomous vehicles, that's important information to know. But recognition goes a lot deeper than that. Voice recognition, translating the auditory signal that I make by creating compressions and rare fractions in the air into a digital signal representing the words I'm saying. Optical character recognition, which is the process of taking handwritten characters, the numbers the numbers 1, 2, 3, the letters A, B, C, translating them into their essentially, I mean, you could call it an ASCII character, but essentially a digital representation, even facial recognition, looking at a pattern in my face that's unique to me and understanding that I am who I say I am. All of these, so every one of these kind of patterns or application areas is as complex. The one we're going to spend a little bit more time on today, maybe even the two, I should say, predictive analytics and decision making. This is really where we get a little bit deeper into supervised machine learning, which we'll talk a little bit about what we mean when we say supervised and what we mean when we say machine learning, and then patterns and anomalies. Typically, patterns and anomalies deals with unsupervised machine learning, which tends to come down to working with unstructured data. If you wonder why I keep looking to my left, there is a family of baby and mama, both groundhogs and bunnies, currently in my backyard. So there's 2 baby groundhogs and like a mama groundhog, and then there's a baby bunny and a mama or papa bunny. So I'm really fascinated and constantly distracted by all the wildlife in my ridiculous wild backyard. So forgive that. So who am I? My name's Ramy. Nice to meet you. Sorry it's a little backlit, but there's no way I'm going to sit inside this evening. I used to run Mattel's innovation program. These days, I kind of just do my own thing. I do a lot of workshops, a lot of facilitation work, pretty wide range of clients. Lately, been doing some work with a company in Japan, which is super fun, except for the 13-hour time difference. So I have actually a workshop tomorrow at midnight. It starts running till 3 a.m. Eastern time. If anyone wants to trade off on that, just give me a call. I do that all through my company. I've got a small team. We're called 1,000 Days Out. That's most of the work we do, is sort of bringing that design lens to emerging technologies. As was mentioned, I teach at a couple of universities, St. Mary's, McMaster, Ryerson, and U of T. And I'm working on a book right now on this exact topic. So hopefully you feel like you're in good hands. And if not, that's what turning off your camera and muting and walking away is for. So let's dive a little bit deeper into what we mean when we talk about how do we create this kind of shared understanding around some of these core topics. So let's go through an overview of kind of the landscape and the key terms. And then I really want to spend a few minutes breaking down how machine learning as a subset of AI solves complex problems. If you've been aware even just of our surroundings and sort of tech landscape in the last couple of years, you've noticed probably that AI and machine learning are used somewhat interchangeably, and it both pleases and offends me at the same time. Machine learning is a branch of AI, but the reason we use it so interchangeably is because almost all of the things we can do that are in this kind of global field of AI these days come down to machine learning. It's what we're able to do now. I want to spend a couple of minutes also giving you a mental model or a set of rules, really essentially a heuristic, for how do we uncover opportunities for machine learning, like what types of problems can we solve. And then we'll close this part off with a real quick preview of why deep learning is changing the game, why it's so exciting, and what it's all about. We're not going to spend a lot of time on this, and forgive me, I hate slides. I typically do workshops with just a whiteboard, but it's a little harder these days. So I won't always explain everything that's visually in front of you, but I'll do my best. As I mentioned, machine learning is kind of this primary subset of tools in the AI landscape, and it deals with the ability of having machines understand mathematical relationships. It's not learning the same way we are. And so for that reason, the term's a little bit abused, right? We think the machine's learning how to do something. It's not. Essentially, it's learning what is the mathematical relationship between a bunch of inputs and an output. So let's talk about what that actually means. This is a super simple data set. This would be a labeled data set. So I know it looks like a really simple table, but I'm going to spend a minute or two explaining what's going on in this table. So we have information about homes. We have the year the home was built, number of bedrooms, number of bathrooms, number of square feet. Then we have a price. Now, you could think of these kind of as inputs and an output, but the world of machine learning has decided to make everything more complex with funny terms. It's sort of like sailing. If anyone here sails, you'll discover very quickly that it's not a rope, it's called a sheet for some reason. and you don't turn right, you go to port. The same goes for machine learning. So we're not gonna, the year built, the number of bedrooms, all of these kind of inputs, we're gonna call them features. And the price, or what I referred to earlier as kind of an output, we're gonna call that either a label or a target. For today, we'll call it a label. There's a minor difference between the two, but you will hear both terms used. So the fundamental problem, if you only take away one core concept around machine learning from this today, it is that machine learning is the process of discovering the mathematical relationship between the features and the labels in a structured data set. So that means, and I don't have my iPad here to write on the screen and jot it down, but if we had a sixth row of data here, and it said 1975, 2 bedrooms, 4 bathrooms, 2,000 square feet, could we predict, and with what level of certainty or reliability, what that price, label, or target should be? That's it. Can we uncover a relationship between these features and these labels, and then use that relationship to kind of extrapolate on future data? That's it. Almost all machine learning falls into variations of this core problem to be solved and this core algorithm. So there's a couple of things you might be noticing. This data set has issues. In fact, it has 3 primary sets of issues. The first has to do with the features. Usually I'd like to ask you guys, but for sake of time, I'll give you the answers. The first issue has to do with the features. We're missing a bunch. For example, where's the home located? A home where I live in Kitchener costs a little bit of a different amount than a home in Toronto, than a home in the Yukon. There's other features, the status of the house, right? The style of home, is it a condo, is it an apartment, is it a freehold? All of these things are kind of missing features. The second, with respect to the data set that we're not complete on, is there's very little data here. We have 5 data points. I'm often asked, how many data points do you need to do machine learning? There's no hard answer to that, but it would be closer to 500,000 or 5 million and not to 5. Depends on the variance in the data and a whole bunch of other factors, but typically we're dealing with hundreds of thousands, if not millions of data points. The third is the one that's a little misleading here. I wrote down price. It's a fairly easy at first term, but what the hell do I mean by price? Is that the price it's sold for? Is that the current market value? If it's the price it's sold for, when was it sold? Is that the assessed value for tax purposes? It's actually a pretty ambiguous term. So a huge part of the challenge of doing good quality machine learning work is this early stage stuff. They call it feature engineering. I really believe that designers and design mindset folks are sadly missing a lot from some of these strategic discussions around machine learning, which is literally why I do what I do, is to advocate for more cross-functional holistic approaches here. Moving on a little bit here, within supervised machine learning, I think it's worth just expanding or kind of double clicking on 2 key terms. One is classification. That is this thing we're looking at this or that or an other thing? It could be true or false, yes or no, cat or dog. It doesn't have to be just 2. It could be cat or dog or mouse or other. But there's a finite number of possible answers. The converse, not really converse, a related area, but a slightly different one, is one where you don't have a finite number. You actually have an infinite number of possible solutions. Regression. This is house prices, because it's easy to imagine that depending on how many bedrooms and bathrooms, there's essentially an infinite number of predicted house prices it could be. So that's supervised machine learning in a nutshell. To recap, the learning part is, I know it sort of takes away the magic of AI when I say this, but it's a mathematical relationship between the features or inputs and the output or the label. That's it. It's just unbelievable how many complex problems we can solve, and how many aspects of kind of our tech innovation ecosystem we can address with that fundamental concept. Let's switch gears and talk for about 90 seconds about unsupervised machine learning. Unsupervised machine learning deals with unstructured data. This is a data set where we might have one that looks very similar for housing prices, except we don't have the price column. And we want to start saying, are there patterns in this data? So if we had a few features about houses, but we just wanted to understand, are there certain groups of houses that fit together sort of in clusters? How do we apply this? Well, one way we apply quite often is association algorithms. If customer purchased item 1, then recommend item 2. If user listened to song A, recommend song B. You can actually think of countless examples of this. I will say, for those who already have some expertise in this area who might be questioning it, most of those algorithms, those association things, use combinations of structured and unstructured, supervised and unsupervised learning. But in general, that's this notion of clustering data. We're going pretty quick over this because I want to get to kind of the good stuff. Not that this isn't good. So how do we actually uncover if a problem should be solved with machine learning? I had a workshop about a week ago where when I went through this, someone actually put in the chat message saying, thank you so much. I need to tell you, the guy worked for RBC. He's like, I need to tell my boss this because she thinks that every single thing that we tackle should be AI to solve it. So I'm going to introduce essentially a heuristic, 4 rules that are, I think, fairly repeatable. I'm going to read them out, and then I'm going to back up, and I'm going to read them out again in context of a particular data set so that they make a whole lot more sense. 1, a human expert could perform the task in a few seconds. 2, it's difficult or impossible to write down the rules. 3, it's easy to get examples of the desired behavior. 4, knowing the rules would enable actions to be taken. I realize full well that this is a very abstract set of rules, so let's do it again. But let's think about it in the context of housing prices. Who would be an example of a human expert when it comes to housing prices? Well, I would say a realtor. And if we constrained our data set to a particular neighborhood or community, the question is, could a human expert perform the task in a few seconds? Remember, the task is applying the label. In this case, it's assessing the price. So the question is, if we constrain ourselves to one geography and we told a realtor all the features, you know, it has this many bedrooms, this many bathrooms, this many square foot, it's on this street, in this location, it's in this kind of condition, could that real estate agent give us an approximation of that price? I would say yes. The funny thing is that the counter side is it difficult or even impossible to write down the rules? So what do we mean by rules? What I mean is, imagine a world in which we just paused here and I asked you guys to write down all the rules to relate features of a home to the price. You would probably write something like, well, for every square foot of size, add $1,000, and for every bedroom, add $14,000, for every bathroom, add $32,000, and if there are a gas stove, add another $1,000. Imagine the process of writing down every rule that relates to features to the ultimate price. I would say it's probably difficult, if not impossible to do. Yet, rule 1 says a real estate agent with their just embedded learning from their career choice could look at those and almost instantaneously give a pretty good approximation of that price. 3rd rule, is it easy to get examples of the desired behavior? What we're talking about here is the historical data. Absolutely. It's called MLS or Zillow or other databases. We can go and look up based on certain features, the previous selling prices of homes. And finally, which kind of brings the 3 together, is knowing the rules would enable action to be taken. To say this is to say, if we could articulate those rules, we could apply that label. If you get a yes to all 4 of these, congratulations, you have stumbled across a problem that is suitable for kind of a predictive analytics machine learning approach. If you ever want to dive deep into this, Catherine Hume has written a wonderful article. I will pass along a PDF of this article to you guys. It's about 14 pages long. It's quite in depth. These rules I've borrowed from her work in this HBR article. It's pretty terrific and much more comprehensive. Okay, the last piece I want to talk about in our little like way too short primer on machine learning, and forgive me, my throat's a little. I had another workshop this afternoon, so I've been talking all day. Deep learning. This is one of my favorite photographs in the world. There's a gentleman named Lee Sedol. He was a Korean grandmaster of the game of Go. If we had a time machine right now, I would take you back to 1997. 1997 was a great year for computer science because in 97, IBM's supercomputer Deep Blue beat the then world grandmaster of chess in a regulation match of chess. It was the first time something like this had happened, and it was sort of heralded as, you know, AI and all of these things. But what's interesting about that is, I don't want to downplay it, but it really wasn't all that much of a feat. And the reason I say that is how Deep Blue as an algorithm or as a computer worked. If you and I put yourself a little thought experiment with me right now, if we were playing a game of chess, the way it would go in my head would be, okay, if I do this, she'll do that, I'll do this, she'll do that, I'll do this, she'll do that. And I get about 3 or 4 moves out before I kind of lose track what the first one was. I can go through one permutation. Well, here's the cool thing. Deep Blue was able to do about 20 billion calculations in the time for one regulation move of chess. 20 billion calculations, for those who don't want to do the math in their head, translates to about 12 moves and counter moves, where the computer would calculate not just 24 moves in the future, but every possible combination of those 24 moves. So essentially what was happening was the computer could see 24 moves into the future, every possible state of the board. At that point, all it had to do was choose which path leads to checkmate or to the best possible outcome. It doesn't work for Go. The game of Go is far more complex. The number of possible move combinations at any given point in time on the board is somewhere around 10 to the 170. For those not familiar with scientific notation, that is a 1 with 170 zeros behind it. I'm telling you right now, you cannot grasp how big that number is, because there's only 10 to the 80 atoms in the entire known universe. And remember, 10 to the 81 would be 10 times as many. This is 10 to the 170. It's an unfathomable amount of complexity in this game. So instead, AlphaGo, which was the Google acquired computer algorithm AI that ultimately beat Lee Sedol in this game, had to learn strategies. And in fact, at one point, it improvised a new strategy that no one had ever done before. And when the human being who just had to do the moves that the computer was telling it to do, did that move, the commentator actually said, "Oh, rookie mistake. That's a strategy no one uses anymore. Lee's certainly going to win this round." In fact, the commentator didn't even comprehend the strategy the computer was using because no human had ever done it before. That strategy is now in textbooks on the game of Go, named after AlphaGo. It is so neat because it actually understands the rules of the game, understands strategies, and uncovers new ones. It doesn't just brute force. I'm not going to spend a whole bunch of time on this, but essentially what's going on, why are we calling it deep learning? Deep learning comes from an area of computer science called neural networks. Neural networks were essentially an early attempt in computer science to mimic how our brains work. We said we have neurons in our brain, they have a whole bunch of dendrites that take information in, they fire, there's a gap between where they fire and the next one, and call that a synapse. It's this network of weights between all of these neurons through which intelligence essentially evolved. Deep learning was this jump to say we need these hidden layers, which the purple, red, and orange layers you're looking are hidden because they don't have inputs or outputs connected to them. I know I'm going quickly here, but essentially intelligence, you could say, evolves as we go through these layers of the network. And so what happens is when we take this picture of a dog, break it down into pixels, feed each pixel into every input on the first layer of the network, as we go through, we identify the edges, we identify combinations or intersections of edges, we identify some of the features, maybe an ear or an eye or a paw, and at that point we get a certain level of certainty with which we can declare, yes, this is a dog. I have taken what is a multi-year process to learn and really implement and explain it to you in 45 seconds, but that's the gist of it. Deep learning, the term deep comes from this notion of deep networks with many hidden layers. They're incredibly powerful though. And we won't even get to talk about how cool and powerful they are. What I want to do now is switch gears a little bit. I want to talk about a couple of practices To try to get a design-minded approach to AI in your various organizations, oh, why am I clicking here? So the three practices we'll talk about, one will be really knowing your data, and what does that mean? The second is making sure to be curious. And the third one is to challenge yourself, challenge your peers, challenge your boss or your mentor to think about KPIs versus FYIs. So the first practice, knowing your data. Training data matters. Okay, so the reason I wanted to illustrate that house price example to you is to articulate this notion that if we had, like I said, 500,000 records of data, okay, and we built an algorithm, that algorithm learned the relationships between the features or the inputs and the outputs of the labels. If we could do all that, it could then predict a future house price. But hopefully it's starting to click for you. The quality of that prediction is only as good as the quality of the data we put in. There's a very old adage, this is way before even the term AI. It was GIGO, it was a computer science term, GIGO, garbage in, garbage out. If you put bad data into an algorithm, bad data will come out. Related to that is this notion of data bias. We're seeing examples of it every day. All of our human unconscious biases, but also data biases in the data that we collect, the data sets that we harness, all of them have the potential to massively, positively or negatively, tends towards more negative, but it could be positive, impact how algorithms work. So let's talk about that for a second. Close your eyes and picture a CEO. And now be honest with yourself in terms of what the first image was that came to your mind. Not what you overruled yourself to decide you wanted the CEO to be, but what your true first unbiased, unconscious thought was. What happened? And I'm not going to make anyone share that. I'll leave that to you to decide what you really felt it was and how quickly you overrode it, or if you had to override that thought. But what happens when we looked, and this image goes back a few years now, but what happens when we search for CEO in Google Images? Anyone want to give me a guess? Well, it looks a little something like this, or looked at one point in time a little something like this. We got Steve Jobs, Jim Balsley, Jack Ma, definitely a few stock photos here and there. And unfortunately, the first female representation of CEO is in fact not even a female CEO. It was a Mattel product called CEO Barbie. Does this happen because all of the engineers and data scientists at Google are sexist? Does it happen because they tend to be more male? Those might be inputs into it, but does it happen because most of our CEOs are male? In fact, as of May of this year, the Fortune 500, anyone want to guess how many female CEOs were in the Fortune 500? Of May of 2020. It's about 31. Single digits percentage. So if we understand this fundamental concept that this algorithm that's being designed, and it is being designed, is learning from the data that's out there, this image, while bothersome, isn't necessarily wrong. It's wrong, but how else should the algorithm know? And I'm not trying to defend it, but I want to challenge you to think about this relationship between where our data comes from and our ability to make predictions, and the role of bias in our data sets. The final part I want to share is this notion that AI can also, in particular machine learning, can help us understand influencing data. And what I mean by that is, not only can we, so if we think of the house price example, if we were to build that algorithm, there's a cool side effect of that. Not only could that algorithm help us predict for the 500,001th sample what the price of the house is, or the value of that house is, if we got all the fundamentals right, there's another really neat thing we can do. It relates to this field, which we won't talk about, but it relates to something called dimensionality reduction in machine learning. But what we're really talking about is understanding the influences. Because what we might find is if we had, let's say, 35 features about that home, the year it was built, number of bedrooms, number of bathrooms, location, zip code, you know, if there's a nest a bird's nest on the chimney, how many fireplaces there are. If we had all these data points, AI can also help us understand which of those data points actually have a correlation, relationship with the price. And that's a really powerful thing as well. So the first piece is really understanding your data. This comes from getting to know the world of data science, unfortunately, the world of statistics. I gave a talk at FITC, like, God, at least 5 years ago, called Why Data Scientists and Designers Need to Be BFFs. I do really think it's quite vital, and it does take some work to do. The next slide will get skipped past quickly. The next two, we spoke about it anecdotally instead. So let's talk about the second practice here. It's a group of designers and design sprint and design thinkers. So I hope I don't have to tell you this, but be curious. And what I mean by being curious, the thing is that AI helps us uncover signals buried in massive amounts of data. But in doing so, I think it's fair to assume and know that inside of these massive data sets, there will be a lot of noise. As a result, I think curiosity and sort of a curiosity-driven mindset is really critical. I don't mean that for you guys. You guys are all designers and product folks and service designers. You're already inherently curious in doing what you do. I do, however, believe that we all have responsibilities to our peers. For example, working with machine learning engineers and data scientists to help them understand how to ask the right questions, what questions to ask, things. It's actually one of the biggest challenges I come across in the work that I do. And what I tend to find is that people don't always know what questions they can or can't or should or shouldn't ask of their data. In fact, it can be a fairly big challenge to understand what those questions are. The third, give me one moment here, because my setup has just changed. So when we talk about this notion of curiosity, I love data points. And when I explain to people why curiosity is important, I like being able to point to a trusted source. This is a terrific HBR article about this notion of curiosity, advocating that it's not only a vital skill, that it's as important as intelligence. I think that the particulars of AI, again, it's a broad term, and that technology relates even more so to complexity than any other technology we've had before. Curiosity is really key, I think, in being successful with this. I think it's something that we all as designers and design leaders can bring into the equation as part of our value proposition. In fact, if you were to read this article, it would even propose the development of something that they call CQ, curiosity quotient. So much like you have your intelligence quotient IQ, emotional intelligence EQ, they're proposing a CQ. Finally, we need new approaches to extract value from and monetize data. I hate the word monetize. It makes me cringe for many reasons. First of all, grammar experts Strunk and White in their foundational book on English grammar, The Elements of Style, would advocate that you can't just add the letters I-Z-E to the end of a word and make it a verb. Just not allowed. Second, monetizing data has to do with creating value for the business or for the organization. So whenever I get a CIO or a CTO asking me, hey, we need to ideate new strategies to monetize our data, I usually tell them I'm not interested in that, but I'll help them find ways to create value from their data. And if you create value for your customers, I think it's fair to assume that there is generally some sort of gain back in for the organization there. So we're going to explore all of these in just a moment, but one of my favorite tools for this as a design tool that gets used in design sprints, in design thinking kind of collaborative workshops, things like that, is cards. I love the tactility of little playing cards. This is a deck of cards I helped contribute to from one organization. We're working on a revision of these, but essentially you're looking at this set of cards. There's three types of cards. The first are interface cards. They are things like beacons, kiosks, cell phones, mobile device, TVs, letters in the sky, whatever it happens to be, different interfaces. The second are related to predictive technologies or types of machine learning AI. So they're actually color coded. You can probably see green, reddish, and blue ones. The green tend to deal with unstructured data. The blue deal with structured data. And I can't remember offhand what the red ones deal with. Oh, they deal with sort of more pattern recognition. And so the idea, and then the third cards are these ones called unexpected bug cards, which are things like bias in the data. But in general, the way it would work is if we're trying to sort of, how might we use AI to solve problem X, Y, Z? One of the ways we encourage participants in an ideation, brainstorm, workshop session to, I don't want to say be more creative, but to feel more creative is by literally handing out combinations of these cards and saying, okay, using unsupervised learning for anomaly detection plus digital kiosks, how would you solve this problem? And we go through literally 2-minute little exercises. You guys are designers. You've all done things like this where people have to come back and you have 2 minutes to tell a story how we use these 3 weird combination things to solve the problem. And 9 out of 10 of the combinations are terrible, but every once in a while we hit on something. We're like, oh, wait, these things together actually create a new solution, and a solution we wouldn't have thought of otherwise. These are some of the tools that we try to bring into this sort of design approach to AI. I'm going to pause here to see if there are any questions. Okay, we will keep going. The third one I want you to think about here is a mental model shift from KPIs to FYIs. Most of us get this wrong. So what I mean by that is, can we actually differentiate between leading and lagging performance indicators? Your organization's sales data from last quarter, while a lovely stat to put up on an executive dashboard, is generally useless information. It either makes people feel good about themselves or feel bad about themselves, but rarely does it give us the ability to make pull any levers or make any strategic decisions about the future. Understanding which these metrics can drive action, that's where we get from performance indicators away from essentially FYIs, for your information. That's where the real change comes. And I think it means rethinking the role of dashboards and reporting. So much of the data and analytics work that is done now, I was working with one of the 5 Canadian financial organizations, and I met with their chief data officer. I didn't say junior manager of data. I said chief data officer. He has a C at the start of his job title. And he told me that what his organization of about 220 people does is create reports for the rest of the organization. And it just hit me. I'm like, well, but aren't you able to do any predictive work to sort of see, where the business is going, where future trends might lie? And they said, nope, we create reports. We're a team of analysts. And that was the role of data. They were just dealing in the world of FYIs. Working with them now to help change that, which is a fun and daunting task. But I really think that this is where we need to go, but it is a mental model shift. And again, this is a shift that I think designers through design sprints, through design thinking. And so we're going to switch careers completely, because I planned kind of for 45 minutes. We're only 2 minutes over of delivered content. And then I wanted to spend the rest of the time actually doing something with you guys. Now that means you're going to have to contribute. So I have no way of knowing who's paying attention and who's not, and that's totally fine. It's also evening time on a sunny Tuesday night. But this will work better if you guys participate. So I'd like to introduce a tool called a confusion matrix, and I'm going to explain what it's typically used for. And I'm going to explain how we use it as a design tool rather than as a essentially performance analytics tool. So what is a confusion matrix? It's okay, we talked about this. Okay, a confusion matrix basically is simply put a very confusing, and I think that's why it's called that. I actually don't know the etymology of the name, but it's a true-false table. We have a prediction that our system makes, and we have the reality in the real world. The system can predict that something is there or not there, and in the real world, it is there or not there. And that leads to 4 possible outcomes. Now, 2 of these possible outcomes are great. When the system predicts that something is true and in reality it's true, it's called a true positive. And if it predicts it's false and in reality it's false, it's a true negative. That's great. Everything is working as it should. Where this gets complex is that when we get a false negative or false positive, they're very, very different types of errors. And the problem with messy data and the problem with predictive technologies, and I truly think it's a design problem, is that there are 2 ways to be wrong. It'd be one thing if it was just right or wrong. But the problem is there's these 2 ways to be wrong, and they're actually opposing forces to one another, at tension with one another. So I want to put this into much simpler terms. I decided that Netflix would be our example for tonight. Netflix, very good at making predictions of what we like. And if there's something new that comes out that it thinks we'll like, it'll put that kind of on the home page or kind of the welcome screen when you turn on your profile. Now so I'll tell you, I really like Back to the Future. I really don't like Downton Abbey. Though to be fair, I've never actually seen it, but I don't think I would like it. When Netflix releases a new season or movie of Downton Abbey and thinks that I won't like it, in fact, I won't like it, I'm a happy camper. I don't even know about it. And when Netflix decides to suddenly, a couple of weeks ago, launch Back to the Future into the library, and it thinks I'll like it, and I do, I'm very happy to see that promoted from me. Like I said, these are the easy cases. Where it gets tricky is, what happens when Netflix releases that new Back to the Future movie, or adds it to their library, I should say, there's no new ones, but it doesn't think I'll like it? Well, I don't actually find out about it. I'm not necessarily upset about this situation. It's sort of a meh result. And what happens when that new season of Downton Abbey comes out? And it's the first thing I see when I turn on my TV. I think to myself, like, Netflix, you don't even know me. Like, how have you not figured this out yet? And so this seems like a joking kind of goofy little scenario, but a big part of Netflix's business model is on the content side, and that content is dependent on them understanding what their users want and promoting that content to those users, and literally even crafting, creating, designing that content to appeal to certain demographics of their user base. If they don't get this right, there are actually massive financial and brand impacts to them, especially in a world where we have now as many streaming services as we used to have channels on the TV, each one for its own $10 a month, right? So I share this as a kind of a lightweight example, but it actually has a very meaningful impact. And I think that this is a design challenge, and I'll explain to you why in a moment. So what principles do we need to have in terms of designing predictive systems? We need a systematic approach to tune an algorithm. We need to measure user and business impacts of our errors. And we need to understand the path or paths for error recovery. So we're going to go through an example now, and you guys are actually going to do this, and I'm going to mute and watch you do it for a few minutes. What we're going to do, and there's about 25 people on here, so we're going to break out into about 4 groups, and that maybe we'll do 3 groups. That'll be, we'll be certain having a handful of active participants in each group that way. I want you to imagine a scenario where we are at a bank or a credit card issuer, and based on historic data, and maybe third-party data like other kind of factors, the bank and the credit card issuer is able to predict whether a transaction is fraudulent or legitimate, knowing that we will be wrong sometimes. The question to you is, how would we tune our prediction engine? What I mean by tune is this. If we are Netflix and we are tuning our prediction engine, what we would be talking about, and this would be ideally a discussion between a product and the design leader and the technical team that's actually creating the algorithms, to say, would we rather, knowing that we're going to be wrong sometimes, would we rather be wrong showing people stuff that they don't want, or missing things that they might like? What's worse to us? We need that systematic approach to decide that. So the idea here is, What we're going to do in a moment is I'm going to switch to a tool called Mural. Some of you may be familiar with it. It's basically a giant whiteboard that we're all going to share. I'm going to post the link to that Mural board in the chat window, ask you guys to jump in there, and then we're going to go into breakout groups and actually go through this exercise in small group discussions and then come back and sort of like take up the exercise. I want you guys in that session to then go and say, let's think about the credit card scenario. You have two things you need to do. The first thing you need to do is identify what are the four scenarios. And I'll tell you one of them right away. A true positive, in the case of credit card fraud, is when the credit card issuer believes that something is fraudulent, and in fact it is fraudulent, and the transaction gets blocked. That's the real world scenario of what's happening in that scenario. There are three more scenarios. I want you guys in your groups to first identify those, and there'll be space on the kind of shared whiteboard here for you to put your notes down. The second, once you've done that, once everyone's aligned to what those are, is to go through, I've created these prompting questions, by no means comprehensive, but they give an idea. What's the customer user experience in each of these scenarios? How will he or she feel with different kinds of errors? Are there different types of users that would react differently? I also want you to think about the business impact. Are there financial impacts to this one type of error or the other? What types of privacy, compliance, or regulatory impacts need to be considered? Are there insurance risk exposure issues to consider? And then finally, and I think most importantly, we'll talk about why when we take it up, is error recovery. When an error occurs, whether a false positive or false negative, how can a user recover? And is the process different for a false positive and false negative? I'll give you a hint, it almost always is. And so generally what you will find as you start to do this, and I find the best way to really learn and let it sink in is to do the exercise, is that most of your time is spent thinking about the situation of false positive and a false negative. So a true positive and a true negative, those are the good scenarios. That's where everything worked the way it was supposed to. The system predicted something, the prediction was correct, everyone's happy. It's when we predict something that's not there or fail to predict something that is there that things kind of go off the rails. And we really need a design mindset to address those scenarios. So with that, I want us to now think of this as a design tool. And so what we're going to do is, this is our design sprint mural board. I'm going to give you a 10-second tour of Mural for those not familiar. We're not going to use all of this. This is part of a much bigger workshop here, but what you can do on the right is if you click on Confusion Matrix, it'll zoom into this area. I'm going to give you the link for this in a second, unless you want to manually write it down from the screen share. You guys can click anywhere. Anywhere you double click, a post note shall appear and you can immediately start typing. If the note's too small, click on it, enlarge it, text will enlarge. Pretty straightforward. I imagine many of you have used this. What you'll find is we have, for step one, all you need to do is kind of put some notes down, and there'll be three groups working in parallel. So you'll see other groups' notes, and that's okay. But we're going to put some notes down about what each scenario represents and what that means. So again, true positive is fraud detected and correct, transaction blocked, customer alerted. That's pretty much it. There's not a whole lot more to say about the scenario. I want you guys to think about the other three scenarios. And then once you've done that, start thinking about these questions below and have a discussion. What I would like you to come back to me with is pretend I'm your VP of credit card AI fraud predicting, and you need to make a recommendation to me to say, when we design our algorithm, our fraud AI cool predictive algorithm, we want to favor fewer false negatives or favor fewer false positives. Essentially, we can avoid one or the other, but we can't totally avoid both. Or you might come back and say, we want a balanced approach that avoids them both equally. The question is, which way in this tension you want to pull it? And I want you to be able to justify that. And then we'll talk about, some of you may discover the method for it, otherwise I'll introduce a more systematic way to do so. So with that, are there any questions about this? Through just the design mindset can bring into organizations when working with data scientists and machine learning engineers. Welcome back. I know that was super short and a little bit rushed. I got to listen in on both conversations, and I love this. I love hearing that, we didn't have enough time for it, but not that that makes me happy, but sort of that you're kind of into it, and that I heard really passionate arguments for why the false negative is worse and why the false positive is worse. And so just to recap, so we're on the same page in this scenario, The false positive is you go to buy something, the bank thinks the system prediction is that it is fraud and therefore blocks the transaction even though it would have been a legitimate transaction. A couple of years ago, this happened quite a bit while traveling, for example, if you weren't in your home country. A false negative, on the other hand, is when a fraud slips through the cracks and you discover it maybe 3 weeks later when you look at your statement, in some cases 3 months later when you look at your last 3 month statement, because you're not looking at them all the time. And you think to yourself, oh wait, I didn't buy that flight from these two countries. Like, where did this $2,000 charge come from? And in that case, so where I see, I'm going to switch here to my pretty pictures here, where I see this becoming more of a design tool. So generally confusion matrices are used to analyze the performance of an algorithm actually. So you will, in each of the 4 categories, do a percentage of where your results ended up, and then kind of have these essentially performance metrics for an algorithm, right? So what percent of yours are false positives, what are false negatives? There's all these different ratios we'd be looking for. And it's certainly good for that. And that's the typical use of confusion matrix. I think it's a terrific design tool. I'll talk to you a little bit about why I think that. So this is essentially what it should look like for the fraud scenario. A lot of people also struggle with the true negative. Well, true negative is a regular transaction that was not flagged by the bank and went through. And in fact, if you think about it, it's probably 99.9% of all transactions. So I'll tell you how I got to this. I was recently having some renovations done on my home, and my contractor allowed me to pay with a credit card. And I was quite surprised. I was like, well, sure, get some points because it's a considerable amount of money. So I called my bank and I got a new credit card issued because the trip's coming up. This was a little while ago. Figured some extra airplane points wouldn't hurt. So I got a new card, lovely little $15,000 credit limit on this card. And so I go to the contractor's office. Even before I went inside, I started dialing the 800 number on the back of the card because I knew this transaction would be blocked. I'm about to use a card for the first time. I'm going to put through at a new vendor that I don't usually buy from. And my first transaction will be for $15,000 even, which happens to be the exact credit limit of that card. It would be almost problematic if that weren't flagged as fraud. So knowing what I know about this industry, I actually started calling in and going through the 800 number ahead of even trying the transaction. So they put the transaction through, it gets declined as I expected. While I'm on hold, waiting, and I actually set a timer because I was curious about how long it would take because I like to investigate these things, felt the phone vibrate, looked down, text message from my friend at TD. Looks like you're trying to make a transaction, didn't say for how much, but it said the vendor name at this location. Are you doing this, yes or no? I wrote back, yes. 1 second later, pops up, the transaction is now approved. Please run it through the POS again. They can't retroactively go back and approve it, but they can say it'll go through the next time. So I went through, lo and behold, it went through. I was still on hold actually when it finally went through. I obviously hung up the phone at that point, but that's when it occurred to me. So yeah, you could say like, every designer in the room would say, yeah, they created a great customer experience. And absolutely, no doubt about that. And it's actually not that complicated on the technology side. But something else occurred to me that's going on in the background in this scenario. The question is, what if we could optimize one error recovery path? So we have false positives, false negatives. What if we could make the error recovery path in one of those way easier? Well, now we actually have a design criteria that we can use against this confusion matrix. We can go through that list of questions and say, we know all the ways to recover from error and false positives. We know all the ways to recover from error and false negatives. Is there one of these where we can make that error recovery path shorter, faster, more frictionless, or reduce the friction? If so, a few magical things actually happen. So in the case of credit cards, and in case of my personal scenario, what actually was going on there? Well, the scenario of a false positive where a real purchase was blocked because it was assumed to be fraud, the bank thought to themselves, and I don't know if they actually went through this thought process, but I like to hope that they did. Hey, we can use a text message to lower the amount of friction that Ramy will face in recovering from this particular type of error. If they can do that, well, they can say, well, since this is a better customer experience and it's less painful, I'm not saying it's perfect. We'd still rather not have the transaction be blocked, but it's certainly a lot less painful than having to call into an 800 number. It's actually a lot cheaper for the bank as well once the capital costs on that system's in place. But there's another piece of this that happens. They can now tune their algorithm to actually be more sensitive. In fact, I would bet that they had tuned their algorithm to allow not for less, but for more false positives. Now, if we had done the deep dive on the way false positives and false negatives work from a real machine learning predictive perspective, we would have talked about the fact that it is attention. And if you have fewer false positives, you will usually have more false negatives, and vice versa. So here's what's really interesting to me. Not only did the bank in my scenario reduce the error path for one, but in doing so, it gave them the freedom to increase essentially the sensitivity of their algorithm, block a few more transactions, but in blocking a few more, they're going to reduce the number of false negatives that are going on. So it's actually a win-win scenario. They're going to reduce the number of false negatives by purposely having more false positives, knowing the false positives aren't that painful, and therefore saving themselves a lot of cost on fraud that ends up slipping through the cracks as well, potentially reducing their insurance costs because banks are insured, of course, against this type of fraud. So it's a really neat way. And the moment it clicked for me that your design criteria, your driving force is towards reducing the error recovery path, that's when I kind of realized that we can actually use this confusion matrix as a design tool. So,
yeah.
So with that, we talked about these things. I want to give you the kind of technical terms for this. This is the last piece here, and this diagram would make more sense if we got a slightly longer session here, but this notion of avoiding false positives or avoiding false negatives, there are technical, like statistical data science terms for it. So if we assume that the blue dots are the things we are trying to classify and the large blue circle is our classification thereof, you can see that in the first example here, I missed two correct answers. So for example, that would be in a bank case, these would be examples where a fraud slipped through the crack, right? I'm trying to catch all these frauds, but two of them slipped through the cracks. This is a case where there are no false positives, but that will mean that there are going to be some false negatives. We call this optimizing for precision. The alternative of this sort of push and pull dynamic is to optimize for recall. In optimizing for recall, we say, we don't want to miss any. So we're going to catch every single fraud that's out there. But in doing so, we'll probably get a few wrong as well. That's the false positive. So in this case, we capture all of the true positives, but we also have some false positives. And I know that the lingo goes back and forth and can be a little confusing. You might just need to stare at this for 5 minutes later on to have it really click in for you. But I introduced this for you for one particular reason. It's to say, as you as product and design and business leaders are thinking about how do you work with data science and technical teams to translate the desired customer experience into an algorithm, if you do this, if you go to your data science team and you say, yeah, we got this predictive algorithm for catching credit card fraud or money laundering or tumors in whatever screening tools, and we want to optimize for precision or optimize for recall, you'll at least grab their attention when you start using some of these terms, which is kind of fun to watch. But more importantly, you can actually have a meaningful conversation about not just how the algorithm should work and behave, but why it should be that way. And I think that what I hope you take away from this is sort of the design mindset and the designer role in all of this work as AI gets more steam and becomes a bigger part of everything we do. And if I haven't convinced you yet of why this matters, I'll share with you one last example here. Before I put up the pictures, this was an example published by the New York Times. It was a collaboration between the New York Times and MIT. And what they were doing is they looked at the gender detection algorithms. These are binary gender algorithms, just for context here. So you upload an image and it will return a result either male or female. And they looked at the algorithms through the context of about 300 images from 4 different population groups, and they tested the algorithms at Facebook, Microsoft, and IBM. Is that correct? Yeah, all use. They're the 3 leaders in gender detection algorithms. What they found was when they put up a data set of about 300 photos of lighter skinned males, I'm using the exact language here from their study, gender was misidentified about 1% of the time. So work that backwards, 99% accurate, pretty good. And with about 300 images of lighter skinned females, gender was misidentified about 7% of the time, okay? And as we went to a similar size data set for darker skinned males, gender was misidentified up to 12% of the time. Anyone want to guess for the 4th one, what our error rate was? Well, you know it's going to be higher than 12 because this would be much less shocking if it were less. Any guesses?
80%.
15%.
23%.
23%. So unfortunately, it's actually a lot worse. It's 35%. And I'm going to tell you why that's so bad. Everyone close your eyes for a second. I can see some of your video up. So close your eyes for a second. And assume we live in a gender binary world. I'm holding up a photo. Is it male or female? And we're going to do this 300 times with your eyes closed. After 300 times, what's your error rate going to be? Approximately. 2 choices, you'd guess around. So blindfolded with no knowledge of the photo, your error rate would be 50%. This AI algorithm's error rate was 35%. So in fact, it's actually worse than it sounds. 35 doesn't sound like that bad of a thing, but it's 65% right. It would have been 50% right if it was just guessing. It's a hair better than a guess. Again, just to hit this home in the last 2 minutes here, it's just not happening because all of these engineers are inherently racist or sexist or have all these biases. We all have our biases, that's for sure. But it's happening because the question I can ask you is, out of this population group, who are there the most pictures of on the internet? And suddenly when you think about it through that lens, if we have more training data, the algorithms get better and smarter and faster and more accurate. And if there are more pictures of white men, or actually use the term lighter skinned males to choose from, the algorithms will get better and faster with that population first. So there's a lot of things we can do to overcome this. Diversity in our teams that work on these tools. We don't really have time to unpack all of that, but I want to share this with you because it relates so much to the technology. It relates to what we're seeing in the world today. And so I kind of wanted to leave that with you as a thought experiment, a couple of interesting data points. And it's a bit jarring, to be honest. So that's it. If anyone has any questions, feel free to jump in now. There's my email address, no sales pitch. Hit me up if you have any questions or anything you want to learn about or chat about or grab a beer. We have a deep dive version of this session coming up, I think next week, actually, with the team from FITC. If you're interested or if any colleagues are interested, let me know. We'll send in friends and family set up for that. But yeah, I just really want to thank you guys for your engagement, especially in the evening time. Huge thanks to the entire AdaptiveX team for all the logistics coordinating and inviting me to come speak at this. This is, I love doing this stuff. I love nerding out about it and talking about it with people who are passionate. So really appreciate the opportunity. Thank you guys again. Drop me a line. LinkedIn's also good too. You can find me there. There's not that many Ramys out there, but this is a lot of fun for me. So thanks again to the
Thanks a lot, Ramy. That was really powerful. So I really enjoyed that talk. I'm sure a lot of us did. We learned a lot. We actually just wrapped up a sprint, and I think that confusion matrix, again, having that discussion, building that shared understanding, making some of those kind of design decisions would have been supremely helpful. So that's definitely going to be a tool that I use in my toolbox moving forward. So yeah, just once again, I really just appreciate you coming to talk to the community.